Hi everyone, today we're going to talk about Fleming's left-hand rule and Fleming's right-hand rule and when to use which one, okay? Let me use 3 questions to talk to you about this thing. Okay, so today the first question we'll look at is actually our molecular paper, okay? So for molecular paper, right, the first question they want you to see is they'll tell you that the fan now will rotate where? Only clockwise or anti-clockwise and clockwise and anti-clockwise. Okay, so rule number 1, how do we usually decide when do we use this thing dikenali sebagai Fleming's left hand and when do we use this thing called the Fleming's right hand? Okay, now actually Fleming's left hand and right hand bergantung kepada a few things. Number 1, you can search for certain keyword. If it mentions motor, usually it's left hand. When they mention the word generator, it is always right hand. Alright, so bermaksud that inside the picture, usually they will give you a battery. Usually, they will also, for the generator, there will be a galvanometer. Okay, why got galvanometer? Because they want you to show where the current is going, because you're going to generate induced current. Okay, so now, of course, if they don't draw the battery, if they don't draw the meter, if there's no motor, no generator, they don't give you any clue. So what is another way you can determine? Okay, the best way to find out Fleming's left hand or right hand, if the question is very tricky, is to always ask yourself, what is the end result that you get? What is the ending that you get? Okay, because in some questions they'll ask you, okay, so where will my electron move? This one, electronics chapter 5. Where will my alpha particle deflect towards? So those are, they are asking you where the thing will move, right? Why the thing will move? Because there is a force. So if the ending is a force, okay, because you see a motor, right, your ending is to produce a force, correct? So therefore, this thing is always going to be Fleming's left-hand rule. So motor confirm force ending lah. Now, if it's a right-hand rule, the ending usually, they will mention something about induced EMF, which is your voltage, and then ataupun they will also say something about induced current. So if you read the question and they say that we are talking about induced one, right? Understood generator, you will take right-hand Fleming rule. Okay, so if you follow my method, confirm it won't be any that tricky one. Okay, so now we come back to this picture, you will see it says that this is an electric motor. So kalau motor, this thing will spin. Why it will spin? Because there is a force. So therefore, if they ask you what is the physics rule to determine the direction of the fan, this one understood lah, guys. This is going to be Fleming's left-hand rule. Okay, so now how to know if is it an or clockwise there? Okay, first of all, this is a dry cell, so this is most likely going to be a direct current motor, and then this motor have to spin the same direction baru the car can move forward, right? Because if the fan flip back and forth, so it cannot move, right? So my solution here is either clockwise or anti-clockwise sahaja, or okay, can, alright, it won't both go both sides. Okay, next, so here I like this question because there's a 3D picture and then there's a 2D picture as well. So I'm going to show you how to do both. Alright. Okay, imagine if they don't give you the 2D picture, they only give you this 3D picture. So remember, this is Fleming's left-hand rule. So where will this thing rotate? Now, first of all, if it's a 3D picture, always find out where is the positive so that you know where is the electric current moving. So my current is going to move here, 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 and this direction. We only focus dekat this wire and this wire only, alright, to find where the coil will start rotating. Okay, we go back to just now punya Fleming's left-hand rule. Okay, Fleming's left-hand rule is FMC. So people who are with me knows that I will say that this is called father, mother, and children. FMC, father, mother, children. So at home, who is the boss? So father boss or mother boss? Obviously, it will be mommy is boss, right? Why? Because if you want to hang out with your friends, right? So you go and ask Papa, can I hang out with my friends? What will your dad say? Your dad will usually say, go ask mommy, right? So mommy is the first one. Like you ask mom, say, okay, dad sure, okay. So magnetic field is the first thing that we see. Force, magnetic field, then middle finger is current. Okay, I'm not going to point middle finger here, of course. Alright. Now, so, okay, now you can see the other camera. How can we use our Fleming's left-hand rule? Okay, so step 1, we check our magnetic field first. So magnetic field will always point from north to south. So magnetic field will always point from north to south. So this finger is magnetic field, so it's going to point this way. It's going to point that way. Okay, guys? So now, if we now only look at here, imagine now you are standing here, you will see that this current is actually pointing away from you. So my middle finger will now point away from me. You can see the middle finger is going in, correct? So my north to south, middle finger going in. So you can see my thumb goes up. So if my thumb goes up, bermaksud that my force actually goes up. Then for this one, imagine if you are here. So now this arrow is pointing towards you, right? So you look at the other camera. So now you will see that my north to south, my this finger north to south is pointing that direction, tetapi my middle finger is pointing towards the camera kan. Okay, so you see that my thumb now points downwards. If my thumb now points downwards, that means that my force actually ke bawah. So my force actually goes down. So this thing will start rotating in this direction. This thing will start rotating in this direction. So this is a clockwise direction. Okay, so my force left, up, right, down. Okay, once you are done with this thing, this is for a 3D picture. Now, 2D picture is slightly more confusing. Okay, why? Because usually they use this thing called a dot and cross diagram. Okay, how to distinguish dot and cross diagram? Okay, now, if this is me, if I'm the person who is going to fire the arrow is moving away from me. So what I will see is a cross. Cross means I will see that the thing is moving away from me because that's the back of it. You faham, right? Okay. Or you can see, according to my right hand grip rule, you will see that my hand here belakang kan sini ada like a cross. Can you see like there's a cross here? See there's an X. So that means that the current is moving away from you. But if it's a dot, it means that the current is moving towards you. Why? Because dot means you kena shoot by the arrow. So that's why what you will see here is a dot. What you see here is a cross. Okay, understand? Can I? Faham? Okay. So what you are going to know next here is actually, so dot is pointing towards away from you. So for the left hand side one, we will do this way, whereby again the same thing, north to south, and then after that the cross is pointing away, so my thumb goes up. See the middle finger pointing away from you, right? If you are this camera, it points away from you, right? So therefore the force goes up. Then kalau dot, this one a bit hard, my hand have to twist a bit. So you see that your arm have to pusing keluar a bit, like your arm have to go out a bit. So you see that north to south, alright, then your middle finger point towards you because it's a dot diagram, and after that your thumb goes down, okay? So my force goes down, alright? Okay, so now what happens next here? We have to draw the whole picture. Okay, this picture has a name on, Okay, we call this as the catapult field, guys. This is a very important keyword. This is actually known as a catapult field. Okay, so what about the catapult field? Apa so special about this catapult field? Okay, you will realize that if the force here goes up, the bottom part must be stronger magnetic field so that the strong magnetic field can push this thing upwards. If the force here goes down, that means the top part punya magnetic field will be stronger. So when we draw a catapult field, we have to show that we are drawing a line that looks like this. So the strong punya area must have more lines. The strong punya area must have more lines, okay? Recommended guys, recommended to draw at least 4 lines. So here you can draw another one more line like this. So there are 4 lines. And then here you draw like mungkin 2 lines. Here you draw like maybe 2 lines. Okay guys, because I want to do this fast, so sometimes my lines will like putus, okay? But make sure you don't draw putus in your exam. And your lines cannot touch each other one. So therefore, this is what we call a catapult field. Alright. Now for more on catapult field, maybe I will say this in a future video. Alright. Now, so what is the change in the energy when there is when the fan rotates? Okay, when the fan rotates, very simple. So akhirnya, definitely it will be kinetic energy, correct? So what becomes the kinetic energy? Obviously, is your electrical energy lah, alright? Now, when I did this question myself, I actually also wrote another one more thing, whereby I put chemical energy as well. Why? Because this thing punya electricity is your battery, right? So the battery produces the electricity produces the kinetic. So this is what I wrote. Yeah, so therefore this is acceptable. Okay. So another one more way how to increase the rotational speed of the fan. Yeah, I think sure, it's actually very simple, guys. Okay, bayangkan why your fan will rotate. Why? Because your fan has a force, correct? So in your happy family, we got, if you want to have more force, means you must have more mother, you must have more children also, right? Correct? So FMC. So here, if you want to have more force, means your solution will be more magnetic field and more current. Okay, I show you how I write. So they'll say increase current. Okay, some of the people don't realize this is actually now not acceptable anymore. Alright, I give you 3 seconds to think, why is this not acceptable? Why cannot write increase current? 3, 2, 1, yes. Because the answer is we have to say increase the magnitude of current. Okay, so this is like they quite menegaskan, but because they want you to state that it is the value of the current. Okay, can like 10 ampere to 11 ampere to 12 ampere like that. Alright, so a question like this is worth 6 marks. So very simple. Alright, in 10 minutes we can settle one question like this. Alright, okay, let's go and see the next question. Okay, there are many more questions that I wish to do, but there's another one more question that I want to talk about. Is actually this one. Okay, it's a Selangor set 1. Alright, so for people who want to look at this question, especially Selangor people, it's quite interesting. Okay, first of all, what is electromagnetic induction? Okay, for people who don't know how electricity is being created, the general idea is electricity is being created by this thing called electromagnetic induction. So maybe you got north-south magnet. Why I write Utara Selatan? Okay, let's say north-south magnet. So in between your magnet, you will have these lines, which we'll call this as, the proper term is called magnetic flux. Okay, so we call it as magnetic flux. So, very used to writing BM, sorry, magnetic flux. So if you take a conductor, which usually is a wire, if you potong through, if you cut through the magnetic flux, you will realize that inside you will produce this thing called induced EMF, which is voltage, and if your circuit is complete, then your induced current will flow. So this process will produce the voltage. Okay, how to use proper terms? So we will say that it is the electromagnetic induction is the production of induced proper word is electromotive force due to change in magnetic flux. Okay, now of course some of them they will say cutting of magnetic flux. Okay, change is a more proper term. Alright, can due to change in magnetic flux. So the change is actually the cutting of magnetic flux. Okay, then next. So when the coil is rotated, when it's found that the galvanometer deflected. So when you pushing, what will happen is in between here you actually have what Jun Hao just now said was your magnetic flux. Correct or not? Alright. Now if you have your magnetic flux here, when you rotate, when you move this wire up and down, or you rotate this down and up, either way, it will cut through the magnetic flux. Okay, it will cut through the magnetic field. Faham, right? Correct? Okay, so what will happen here is actually cutting of magnetic flux, but we say change. So you can see that as coil is rotated, as your coil is rotated, the wire moves and cuts across the magnetic flux. Okay, try to be more specific. Siapa punya magnetic flux? Magnetic flux of the permanent magnet. Alright, so very important. Of siapa? Of the permanent magnet. So some teachers will say that you never tell me whose magnetic flux, because sometimes maybe there are more than one object inside there. So therefore, permanent magnet. Okay, cuts across the magnetic flux of permanent magnet. So, full stop. 2 marks, 2 sentences. Then we can say that the cutting of, or you can say the change in magnetic flux causes induced EMF, which is EMF is your electromotive force, and induced current to flow across where? Across the galvanometer. Okay, so you have to tell me it flows across the galvanometer, baru the galvanometer will deflect, right? Correct. So yeah, very important. Okay, so you get 3 marks. You tell me the definition, then you tell me the 2 marks on that. Okay. Now, what if we want to make this a bit more interesting? Okay, for example, okay, let's just try to learn how to find the direction of the current. Okay, so now will your current here flow from, let's say I use pink color, A, B. Okay, so will my current flow from A to B ke daripada B to A? If let's say I now move the magnet, I move this wire upwards, so the motion goes up. Okay, so which will be the direction of my current zone? Okay, so right now, because this is a generator, so what we are going to use is our right hand Fleming rule. Okay, so look at the other camera. So right hand Fleming rule is that from north to south. Okay, now remember this finger, mummy is boss. So we will point from north to south because your north to south is this direction. Okay, now what is happening to the wire? This wire is going to move all the way upwards. So you will see that when my magnetic field is going to the right hand side, my force goes up, correct? My force goes up. You will see that my middle finger is now moving away from you, right? Correct. Okay, so you will see that the current is now moving away from you. So the current will flow from A to B, macam ni. Okay, which to be more proper, we will call this as the induced current. Okay, we'll call this as induced current. Okay, next. So how can we increase the angle of deflection of the galvanometer? How to increase the angle of deflection of the galvanometer? Okay, so here we're going to talk about this thing called the number of coils. So if you have one wire, you tarik down, you have one cutting. If you have two wires, you will have two cutting, correct? If I put another wire here, if I tarik, I'll have double cutting. If I put another third wire, I'll have 3 cuttings. So when you have more number of coils, okay, so the answer obviously here is more number of turns, or you can say to increase the number of turns. So what's the advantage of doing this? Is so that we can increase the rate of change of magnetic flux, which is the increase the rate of cutting of magnetic flux. And then after that, so that I can increase my induced current flow. Here, obviously, I can use induced current because already tell you galvanometer. Okay. Then next will be cross-sectional area of the wire. Okay, cross-sectional area of the wire obviously is talking about this part. Correct? It's talking about the whole thing. Okay, what will your cross-sectional area of the wire affect? What will it affect? So obviously it will affect how much current is allowed to pass through. So what it affects here is actually the resistance of your wire. So you don't go and memorize everything is increased change of magnetic flux. So this one is they relate back to your electricity. So here we want a larger cross-sectional area. Okay, for people who don't know, the larger your area is, more current can flow. So therefore this will cause what? We can reduce the resistance of wire, so to increase your induced current flow. So at the end, this will also go back to increase your induced current. Okay, but then recently there is another fashion, there's another trend. Okay, they say, teacher, I realize sometimes, right, some books will use the word resistivity. Teacher, why sometimes some books I see they say increase or reduce the resistivity? Then why sometimes you use resistance? So should we use resistivity di sini here? Okay, can you all leave me a comment? Alright, I'll leave the answer in the comment section maybe a while later, and I want to see what you all think. Can we use resistivity here? If yes, then why? If no, then why? We'll see who have the better comment. Alright. Now, so to increase the induced current. And then finally, the last one, okay, so can we write resistivity here? And then after that, next is the strength of the permanent magnet. So obviously we want a stronger permanent magnet. Okay, why stronger permanent magnet? Because the stronger your permanent magnet, the more magnetic field lines you have. Okay, bayangkan now this one got 5, 6, 7 magnetic field lines. So you have a lot of magnetic field lines, magnetic flux. Versus if I've got another north-south magnet, Chin-Chai only 2 lines like that. So if I take one wire, if I cut through this, I cut 7 magnetic flux. This one I cut maybe 2 magnetic flux. So let me ask you, which one produces more cutting, more change of magnetic flux? Obviously this one, right? So your answer will still go back to the same concept. So if you have stronger permanent magnet, you will increase the rate of change of magnetic flux. Alright. Now, don't just say increase the change of magnetic flux. You want to say to increase the rate of change because you do one action. Okay, it's like your frequency of cutting will increase. Why? Because you do one action, you cut more. So therefore, the rate of change of magnetic flux, and ultimately this will also to increase your induced current. Okay, why I like to write this belakang part? Maybe some people will say it is not needed, but I want to remind myself so that every time when I write, I know that this galvanometer is because you're induced current. So every answer here will always be related back to why my galvanometer will have more deflection. So that's how I remind myself. Okay? Now, so this is a relatively short video. Okay, for the future part 2, I will talk more about transformers and also another quite trendy question, which is about electromagnetic induction stove. Alright, so please do subscribe. I'll say more on this kind of latte hunt in our next electromagnet video. So thank you everyone.